Okay, so one of the topics that a lot of people find tricky is implicit differentiation. So implicit differentiation is used when we can't solve the equation for y before taking the derivative. Previously, when we were doing explicit derivatives, we didn't even know we were doing explicit derivatives, we were saying, hey, if y is equal to 3x squared, then the derivative of y is going to be 6x. And we're just taking that derivative because y is isolated, so we know the derivative of y is y prime. And since we're actually taking the derivative with respect to x, we could apply that on the right-hand side as well. So this is not the same thing as a partial derivative, which you're going to look at later on, but we're looking at equations like the one we have here, okay, where I've got this y to the 5 plus y plus x is equal to 10. So this is an equation that I can't really rearrange and have y equals, and it's asking us to find dy dx. So if it's asking us to find dy dx, there's a couple of things that are coming into play here. So this means two things for us. The first thing is that we apply our derivative rules directly to x. So this tells us that if we have something like 3x squared, that the derivative of 3x squared becomes 6x, just like above. It also means that for most of us, we like to write y prime instead of dy dx. And so we want to keep in mind that the derivative of y is y prime. And so that second point becomes the most critical point we have here. What we're saying is that if we knew that y was equal to 3x squared, like we had above, that we could take the derivative and we could say, hey, the derivative is 6x. But if we don't actually know what y is what y equals, we're just going to denote the derivative of y as y prime. So, for example, we're going to actually do the full example that we have above this y5. But if I have y to the 5 versus if I know that y is equal to 3x squared to the 5, if I was taking the derivative of this right equation, the 5 would come down. I would leave the inside, so that 3x squared, I would have a 4, and then I'd multiply it by the derivative of the inside, so that's 6x. So all we're doing with implicit differentiation is saying that we don't actually know that y equals that 3x squared. So if I have y to the 5, that 5 is going to come down. I'm going to leave the inside, which is just y, and then the derivative of the inside is y prime. So really all we're doing here is applying chain rule where we don't know what the inside equals. So if I have the function from above, y5 plus y plus x equals 10, and I take the derivative, so that y to the 5 is going to become 5y to the 4 times y prime. And again, this is really just me using chain rule where I don't know what the inside equals. So I'm saying, hey, the derivative of the inside is just y prime plus y. So the derivative of y is just y prime plus x. The derivative of x is 1 and the derivative of 10 is 0. The thing that most people actually have trouble with is the final steps of the problem where we need to get y prime by itself. So first off, we want to bring all the y primes to one side, anything that doesn't have a y prime to the other side. So for us here, this is just us bringing that 1 to the other side, so it's -1. And then you want to factor out y prime. We always want to get to the point where we can just factor out a y prime. So I'm going to have y prime multiplied by 5y to the 4 plus 1. I'm just pulling out a y prime from each of those terms equals -1. And this allows me to divide out whatever I'm multiplying y prime by. So I can divide both sides here by this 5y to the 4 plus 1. That's going to cancel. And my final answer here is that y prime is equal to -1, 5y to the 4 plus 1. We don't have to go any further than that. We just need to make sure that we have y prime equals. So we're going to step it up a notch. Now it says we'd like to take the derivative with respect to x. So derivative with respect to x, again, just means our dy dx, meaning that the derivative of y is going to be y prime of this ln y x times y. So I'm going to have this ln y equals x times y. And when I go to take the derivative of ln y, the derivative of any ln is 1 over whatever's inside the ln. But then I'm going to multiply that by the derivative of the inside. The derivative of y is just y prime. On the other side, I'm going to have to be a little bit careful because when we go to take the derivative, we have to remember that this is going to be product rule. We don't actually know what y, the function of y is, right? It could again be that 3x squared, but we're taking a function of x and we're multiplying it by another function of x. It just turns out that y is an unknown function of x. So we're going to use our product rule. So that product rule, we're going to take derivative of the first. So the derivative of x is just 1, leave the second, plus leave the first, derivative of the second, y prime. Once we've actually taken that derivative, we want to collect those y primes. So if we're collecting y prime, I've got this 1 over y prime, and I'm just going to bring this other term over. It's going to have minus x y prime is equal to just y. I'm just dropping that 1 there. And then again, we want to factor out our y prime. So if I pull out that y prime, I'm left with 1 over y minus x equal to y. And then I can divide. So y prime is going to equal y 1 over y plus, oops, not plus, minus x. That's a little bit messy with the fraction on the bottom, but we don't have to simplify it further, so we should just leave it like that. Okay, so now again it asks what's the derivative with respect to x of e x to the y plus 3x cubed plus 2y. So we're getting a little bit trickier here. And so we have again e to the x times y is equal to 3x cubed plus 2y. So when we go to take the derivative, again, remembering that when it asks us to take the derivative with respect to x, all this is telling us is that the derivative of y is y prime, and that we're going to apply the derivative rules to x. So on our left-hand side here, the derivative of e, so when we go to take that derivative, the derivative of e is always just itself times the derivative of the exponent. And the derivative of the exponent is going to be a product rule. So derivative of the first, 1, keep the second, y, plus keep the first, x, derivative of the second, y prime, very similar to what we did above. On the other side, 3x cubed, well, we apply the derivative rules to x, so we're going to have that 9x squared plus the derivative of 2y is going to be 2 times y prime. Right? If we take the derivative, if it had just been the 2x, the derivative of 2x would be 2. But with 2y, the derivative is 2 times the derivative of that inside, right? Because think about it, if it had been 2y cubed, we would have brought that cubed down and then had y squared times y prime. But just because it has no exponent, the rule stays the same, because really what that exponent is 1. where that 1 is coming down, the derivative of y becomes y to the 0 times y prime. And it just turns out that y0 is just y. So it gives us this 2y prime there. And again, we're going to want to be able to collect our y primes. Before we do that, it's a good idea to try to expand this e term so we don't have any weird multiplication going on in the problem. So I'm going to have y to the x times y plus x y prime e to the xy. I am not going to do anything on the other side. And now we can collect our y primes. So when we collect our y primes, again, we're just bringing any term that has a y prime to one side, any term that doesn't have a y prime to the other side. So I've got this x y prime e to the xy minus 2y prime is equal to 9x squared minus y e to the xy. And now again, we're going to factor y prime. So if we factor our y prime out, I'm going to have y prime x e to the xy minus 2 equals to this 9x squared minus y e to the xy. And in our final step, we're just going to divide so that we can isolate for y prime. So y prime is equal to whatever we had on that left-hand side divided by x e to the xy minus 2. Okay, once more, what is the derivative with respect to x of e to the 2x plus 6y squared equals y ln x? So in this problem here, again, we're going to take that derivative, and we don't have a y equals equation. This is implicit differentiation, meaning that the derivative of y is y prime, but we can apply the derivative rules to x. So the derivative of this left-hand side, the derivative of e is always itself. So e 2x plus 6y squared. But then we have to take the derivative of that exponent. This is not a product rule like last time because it's separated by an addition. So the derivative of 2x is just 2, but the derivative of 6y squared is going to be 12y. And remember, anytime we use a derivative where there's a y, it's actually chain rule. So we leave that inside, which is y alone, and then we multiply it by y prime. On the right-hand side, we do have a product rule, right? Because we have two functions being multiplied together. This is our product rule. So the derivative of the first, the derivative of y is y prime. Keep the second. Plus, we're going to keep the first. Derivative of the second is 1 over x. So if we're not really good at our core derivative rules, this can be a very overwhelming process if we can't remember, that the derivative of ln is 1 over whatever's in that ln, or the derivative of e is itself times the derivative of the exponent. So if you're finding those are difficult, it's really time to go back and review our core derivative rules and practice those until we are absolutely solid. Implicit differentiation is not that tricky once we know our core derivative rules, but if we don't know those yet, this can be a very daunting problem. So once we have that derivative, again, we're going to want to get all of our y's together. Anytime we've got this kind of bracket situation, we're going to want to expand this so we can collect the y prime. So I'm going to have this 2e to the 2x plus 6y squared plus 12y y prime e to the 2x plus 6y squared. And nothing's changing on the other side of my equation here. And now I'm going to bring everything with a y prime over. So we're going to collect the those y primes on one side. So I'm going to have my 12y y prime e to the 2x plus 6y squared minus y prime ln x. And on the other side, I'm going to have this 2e to the 2x plus 6y squared plus y over x. Our next step is always just to factor y prime. So if we're factoring y prime, we're just pulling up that y prime, multiplying it by whatever's left. So that's going to be 12y e to the 2x plus 6y squared minus ln x. We really don't care how messy this is because the factoring is always going to work out for us so that we can get y prime by itself. And that's the goal. We don't need it to be a pretty equation. We just need it to be y prime equals. And so then we're going to divide. So y prime is equal to 2e to the 2x plus 6y squared plus y over x. And we're going to divide it by that entire term that we are multiplying y prime by. So our 12y e to the 2x plus 6y squared minus ln x. And there we go. So one of the things that we're going to use implicit differentiation with is in combination with logarithmic differentiation. So we just want to recall some of the rules of ln. And so ln, if I take the ln of e and I put this in my calculator, I'm going to get back 1. If I take the ln of two numbers being multiplied together, this becomes ln of a plus ln of b. So if I have ln of 6, that is the same thing as ln 2 plus ln 3. If you put that in your calculator, it's so interesting because that ln 6 is going to give us back a 1.791759. It goes on for a very long time. And if you put ln 2 plus ln 3, because 2 times 3 would give you 6, into your calculator, you get back the exact same number. If we have ln to some base and their exponent, this is the same thing as bringing that base out front of that ln a. So if I had something like ln of 2 to the 5, this is the same thing as 5 times ln 2. Oh, I have an example right here, right? If I have ln 5x to the 7, right? So this multiplication is going to become addition, and then my exponent is going to come down and out front. So I'm going to have a ln, we always do the multiplication first, so ln 5 plus ln of x to the 7. We split up that multiplication, but we can go one step further because it's going to be 7 ln x. That's equivalent. And so we often use lns to help us solve for exponents or bases in weird situations. Lots of people ask me, like, well, what does a ln actually mean? So ln is just a function. So if I have a value of x and I put that x into the ln function, I get back a number. Now, if I put in my calculator a negative value, so I have my y and my x here, if I put back in a negative value, it is undefined. It does not exist. If I put in ln of 0, it's also going back undefined. And what we end up with is this function. So if x is 0.001, so really, really close to 0 there, the number that equals negative 4.6, and then negative 2.3 when it's at 0.1, and then by the time it gets to be 1, it actually crosses over at 0. And basically what we have here is a function that doesn't exist for negative values of x, and that it's going to increase very slowly. So at x equals 2, this value is I have not drawn this to scale, but our value here is 0.69. And a value of 10, this would be 2.3. And at a value of 100, so way, way off on our chart, it only goes up to 4.6. So it's very slowly increasing function. And so we use ln to just, in general in this class, help us solve for exponents. So if I have 15 equals e to the x, and I want to know what x equals, I'm going to take the ln of both sides. I'm going to use my ln of 15 is equal to, and when I apply, ln e to the x, because whatever we do to the left side, if we do to the right side, the equation stays equal. So I'm just ln'ing both sides here. But really what this ends up being is that ln 15 is equal to x ln e. And we know from above that ln e is just 1. So we know that x is equal to ln of 15. And that is just a number. You can put ln 15 into your calculator and you're going to get back a value of 2.708. And it continues on from there, but we'll just leave it at 3 decimal places. It doesn't have to be base e, so I've got this 25 equals 5 to the x. Again, if I take the ln of both sides, I'm going to have ln 25 is equal to ln of 5x. But I can use my ln distributing rules. So I've got this ln of 25, which is just a number, and my x comes down, so then I've got ln 5. And I can solve for x by dividing both sides by that ln 5. So x is going to equal ln 25 over ln 5, which again are just terms that can go into your calculator. And so if we take that ln 25 and divide it by ln 5, we're actually going to get x equal to 2. And so we use this to help us tackle tricky derivatives in something called logarithmic differentiation. So here it asks me to find dy dx of y is equal to 25x to the x. So the thing about logarithmic differentiation is that you must use it whenever you have an x in the base and in the exponent. We have no derivative rules to tackle an x in the base and an x in the exponent. This is totally on us, okay? We've got to figure it out. And so if I want to figure out the derivative, if I have y is equal to 25x to the x, and I want to take the derivative of this, I have to first simplify. There's no rule that allows me to take the derivative when I have an x in both the base and the exponent. We just don't have that. So we start by taking the ln of both sides. I have ln y is equal to ln of this 25x to the x, but remember there are these beautiful ln property rules. So this is going to become ln of 25 plus x ln x. And we can take the derivative of both sides now using our implicit differentiation. So we've augmented the problem ourselves. We've gone from something that was y equals to something that isn't y equals, and we still want to take the derivative. So we're going to do that by doing implicit differentiation. The nice thing about logarithmic differentiation when we're doing this is that it pretty much always follows the same pattern because it's going to be ln y on that left-hand side. So the derivative of ln y is 1 over y times y prime. Again, it's just our chain rule. The derivative of ln is 1 over whatever's in that ln, which just happens to be the y, and the derivative of y is y prime. On our other side here, remember that ln 25, this is just a number. You can put ln 25 into your calculator and it's going to tell you it equals 3.218875. But because it's just a number, the derivative of just a number by itself with no x's is 0. Now the x ln x, This is our golden product rule. So the derivative of the first is 1, keep the second, ln x, plus keep the first, derivative of the second, 1 over x. So just to simplify this, we've got 1 over y prime is equal to ln x plus 1. And just like before, now we don't have to factor out the y primes because there's only a single y prime in this problem, but we do need to get y prime by itself. So we're going to multiply both sides by y so that we can get rid of the y on that side, and we're going to have y prime is equal to ln x plus 1 times y. Now, when it comes to logarithmic differentiation, we actually know what y equals. So we're going to put that back in for our final answer. We know that y was 25x to the x. So we can put that back in, and that becomes our final answer there. Now, one of the exam style questions they like to ask, it's not guaranteed, but it's on a lot of exams. Y is equal to x to the x to the x. So this isn't just one base and an exponent, but this is a double exponent. So when we see this, we actually want to start by just solving y is equal to x to the x. So if I take this, I'm going to ln both sides. I'm going to have ln y is equal to ln of x to the x means the x comes out front, and I have that base x. When I take the derivative of ln y is 1 over y times y prime, and I've got that same product rule on the other side that we saw above, x times ln x. So we're going to have derivative of the first times keep the second. So the derivative of the first is 1, keep the second, ln x, plus keep the first, so just an x, and the derivative of ln x is 1 over x. It's nice to simplify this down, so just that ln x plus 1 there. And of course, we want to, because we have this 1 over y on the left-hand side, we're going to multiply both sides by y. And because we happen to know what y is equal to, we put that back. So this is very important. This is saying, hey, if I know x to the x, then the derivative of x to the x is this ln x plus 1 times x to the x. And you're like, okay, but why did we just do that, Dalton? You're insane. It makes solving the actual y is equal to x to the x to the x a little bit simpler. We don't have to do a double ln, because right now, in order to solve this, if I take the ln of both sides, I end up with ln y is equal to this ln of x to the x to the x, and what happens there is that I end up with the exponent comes down and out front, and this is okay for us because we actually know what the derivative of x to the x is because we just found that. But if I didn't know what that derivative was, I'd have to take the ln again. So I'd have ln of ln y is equal to, and this is going to get split because it's multiplication into addition. So I'm going to have x ln x plus ln of ln x. And it starts to get a little bit trickier when we go to take our derivatives. So we don't want to have to do tricky derivatives, so we kind of break it down into these two steps where we solve just the x to the x like we did on the left-hand side there. And now we're going to solve this question on the right. So the derivative of ln y, of course, is just 1 over y prime. And then what we have here is our good old product rule. except that we know the derivative of the first, the derivative of x to the x, we can just write that down as ln x plus 1 x to the x, right? This is our derivative of x to the x. We keep the second, so times ln x, plus keep the first, derivative of the second, 1 over x. And now we're just going to rearrange. So we've got that y prime is equal to our ln x plus 1 x to the x ln x. I could multiply this through a little bit more, but I'm just trying to keep things as simple as possible right now. And I want to multiply this entire thing by that y. And then I just want to substitute back in for y. So it looks like a real crazy derivative. Absolutely. But you've just taken it. And if this question comes up on the exam, you know, that's 5 to 8 marks that you are absolutely able to handle. So when it comes to logarithmic differentiation, it's used in these type of technical questions where when they show us a question, they say, hey, take the derivative of this. We can't because there are variables in the exponents as well as the base, right? If it had just been y is equal to 5x, we can take the derivative of that, right? It's 5x times ln to the 5. That's okay. But what's not okay is if it's 5 times x to the x. Oof, nope, we have to take the ln in order to solve that. But there's also a word problem that goes along with this. And this is notoriously known as the money stock problem. Now, the money stock problem might actually be a money stock problem on your exam, or it might be, honestly, any equation in the world where we have multiple terms being multiplied together, perhaps with exponents. So in the money stock problem, we have MD, which is the demand for nominal money balances, the money stock, and it is a function of real income, Y, an index of interest rates, R, and an index of prices, P. And they would give you the definitions of what the variables are on the problem. What they might not give you is the definition of percentage rate of growth. This is very important. Percentage rate of growth is the derivative with respect to time divided by the variable. So if we're talking about the percentage rate of growth of M, of the money stock, that's the rate of growth of M divided by M. That's how you turn it into a percentage. Rate of growth is just the derivative, but if I want it to be a percentage, I need to divide it by the total, which is M. So mathematically speaking, this would be the derivative of the money stock with respect to time divided by M. Now, if you look at our equation, there's no t, there's no time in the actual equation, but it's implicit. The money stock, the real income, the interest rates, the prices, that they're all changing with respect to time. So your approach to the money stock problem is actually going to be the same pretty much regardless of the question they ask you about the money stock problem. So here we've got two classic questions. A says if interest rate and indices of prices do not change, but real income increased by 5%, what is the percentage growth of the money stock? If real income increased by 5% and interest rates fell by 3% and prices increased by 1%, what is the percentage growth of the money stock? Whether we're answering A or B, our approach to the solving this problem is going to be the exact same. We're going to do two things. One, we're going to ln the equation. And then two, we're going to take the implicit derivative with respect to time. And again, we don't actually see that t variable. It's not explicitly a part of the problem. So we're going to use that whole implicit differentiation situation, right? Where the derivative of y is going to be y prime, except in this case, y prime is the derivative with respect to time, not x. So if I have that money stock equation, I've just repeated it from above here. Again, our first step is going to be to take the ln. And so when I take that ln, I'm going to have ln of m is equal to, and remember that all of our multiplication here becomes addition. So I'm going to have ln 2 plus, and when I have y to the 0.6, that 0.6 comes down, and so then I'll have ln y minus 0.3, just because I'm bringing down that negative 0.3, ln r plus ln p. So now I'm going to do the implicit differentiation. And remember, this is with respect to time. So this is all, you know what, we don't actually know how these variables are changing with respect to time, but we can use our rules of implicit differentiation. So the derivative of ln m is going to be 1 over m, and the derivative of m you could write as m prime. I could also have written this as the derivative of m with respect to time. Doesn't matter how you do it. The derivative of ln 2 is 0, so you can ignore that, plus 0.6 ln y, so that's going to be 0.6, 1 over y, derivative of y, minus 0.3, 1 over r prime, plus 1 over p prime. And again, you could also write this using the formal notation of the derivative of y with respect to t, or that derivative of r with respect to t, derivative of p with respect to t. Because in this situation, all we're saying is that these derivatives, that all of our variables are changing with respect to time. That's what we're getting at here. And the amazing thing about this, right, if we look at our function, remember, the percentage rate of growth of m is just the derivative divided by m, and that's exactly what we have here. So this term here is that percent rate of growth of m, and this term here is our percent rate of growth of y, and this term here is the percent rate of growth of r. And this term here, yep, you guess it, percent rate of growth of p. So when we look at a question like A that tells us interest rate, and so the interest rate is r, so it's telling us that the interest rate and indexing of prices do not change. So what that's telling me is that the percent rate of growth of r is equal to 0, and the percent rate of growth of p is also equal to 0. But it's telling me real income, and so again, going back to your variables, real income is y. Real income increased by 5%. So the percent rate of growth for y is going to be 5%. And it wants to know, well, what is the percentage rate of growth of the money stock in that situation? So all we're doing there is saying, hey, this dm dt divided by m, that's actually the same thing as the line above, is equal to 0.6 times, well, what's my percentage growth rate of y? 0.05 minus 0.03, my percentage growth rate of r, well, we said that was 0. The percentage growth rate of p, we also said is 0. So our answer here of 0.03 is telling us that in this situation, the percentage growth of the money stock is an increase of 3%. And honestly, we don't care what information they give us. So in part B, if we look at what's going on in part B, it says if real income increased by 5%. So real income is Y. So this is our percent growth of Y is 5%. And then it tells us interest rates fell by 3%. So interest rates is R, and they went down 3%. So that percent growth of R is negative 3% because they went down by 3%. And prices increased by 1%. So that percent growth of P is 1%. And we again want to know what that percentage change of the money stock is. Well, that change in the money stock, right? 0.6 times what is my, 0.6 here times what is my percentage growth rate of Y? And my percentage growth rate of Y, we said was, 0.5% again. Minus 0.03, what's my percentage growth of R? Negative 0.03. Oops, I put an extra 0 in that first one. I'm not supposed to. And then that percentage growth rate of P, well, that one doesn't have a coefficient, so I'm just putting that 0.01 there. And you can see that it really doesn't matter what numbers they give you. You can always handle putting them into this equation. And so this gives us a change here in the money stock of 0.049. So with these changes that are happening, we're saying that the percentage growth, and if it was a negative number, because it'll come out to be negative, it would just mean that this was a decrease. But here we're going up of the money stock. Is an increase of 4.9%. And there you go.